Thanks. So yeah, so I've been putting the links to all the handouts regularly. So today we will start with NFA. So in the last 2 weeks, what did we do? Like we had an introduction of the course, and then we also looked at DFA, and then we started with this thing which was about, if you recall, if you recall, 1 second. I think I can use this. Just a moment. Okay, so we had an introduction to the course, and then we talked about deterministic finite automaton. And then we looked at the end, we looked at these things like the closure under perfect shuffle as well as closure under shuffle, right? And what we found is that when you were constructing the automaton for shuffle, so you were given this language L. So what was the definition of shuffle? Bikhan, can you tell me what is the definition of shuffle? Right. So we have it here. So for example, so this is the definition of perfect shuffle. We were given two languages, okay, A and B. And how are we defining the, oops, I think sort of, okay, sorry. So we defined first perfect shuffle. So what is the idea of perfect shuffle? So you are given two languages A and B, and these are subset of sigma star, and perfect shuffle of AB is, so W equal to A1, B1, A2, B2, AK, BK, where the string A1 to AK, the string A1 to AK belongs to this language A, and the string B1 to BK belongs to this language B. And we are saying that AI, BI, these are the letters. So this belongs to this alphabet sigma, right? So now the perfect shuffle is like you are having one letter from each of the strings. So you have A1, then followed by B1, A2 followed by B2, and so on, correct? And then Bikhan, can you remember, can you tell me how did we construct? So given, so the question was the following. So if A and B are regular, if A and B are regular, then is the perfect shuffle of these two regular languages also regular, right? And we saw that indeed you can construct deterministic finite automaton starting from two DFS corresponding to A and B. So is the question clear, Ankit and Tefila? So the definition of perfect shuffle, and we are trying to look at, thanks. So we are trying to look at the closure under perfect shuffle for regular languages. And then we also defined the notion of shuffle. Now the difference between shuffle and regular shuffle is that here you have AI, BI belongs to sigma star instead of AI, BI belonging to sigma. Okay, right? So AI, BI belongs to sigma star instead of AI, BI belongs to sigma. And then what we saw is essentially like instead of a deterministic finite automata, if you think of this in terms of a non-deterministic finite automaton, then it will be easier to sort of think of this, right? So sometimes it is easier to think in terms of non-deterministic finite automaton. So just to recall a bit more, since we have Ankit and Tefila here today. So how did we, so given, let's say, an automaton DA for the regular language A and DB for the regular language B. So essentially it means that the language DA is A and L of DB is B. So the question was, how do you construct an automaton, let's say D, which accepts the perfect shuffle of A comma B, correct? So how do you construct this? So what we saw is like, so it has to, for example, it will first, let's say, read A1, then it will have to read B1. And what we discussed, so suppose you have a state space here, which is Q of A. So this is the state space of dA, this is the state space of QB, and then we say that you can have a state space of the automaton D, which is of the form QA QB cross 0, 1, right? So, so what is the idea? So can one of you tell me, Ankit or Tefila, like, so what is the idea here? Why do we have such a state space? So I think
it is like a product construction, right?
Yeah, it is like product construction. And so what are we saying? So you have a state, let's say QA comma QB, correct? And then the 0 or the 1 here, it will essentially remember whether it is A's turn or it is B's turn, correct? So you can say initially, maybe your initial state is like this. So QA, I can say QAI, QBI, and let's say I start with this 0, and then it will read the A1, okay? And then it will just change the state corresponding to this automaton. So let's say you had something like this, QAI on A1, it goes to, let's say, Q0. So you go to Q0, and here, okay, so you have QBI, so you will go to Q0, then this state will remain the same, and here you will switch it to 1, right? In order to remember that the next time you'd like to make a move corresponding to the B automaton, right? The DB automaton, correct? And so what we saw is that this produces a DFA, right? The perfect shuffle would produce a DFA to this automaton. Whereas now, if you consider shuffle instead of perfect shuffle, then perfect shuffle, then what happens? These AIs, so for example, these AI, BIs, these are actually strings in themselves, not a single letter, but these are strings in themselves. Okay, good. So in that case, you are going to non-deterministically, so you can think of this. So you are going to non-deterministically read this string AI. So it's now AI belongs to sigma star. You are going to read this for a while, and until again the non-deterministic automaton would decide to switch to the B automaton, correct? And make the transitions on the B automaton. Is it clear? Like, so the non-determinism actually helps here. So I'm assuming that you have some familiarity with deterministic and non-deterministic automaton, but if not, just bear with me. So we will study today the non-deterministic automaton, because sometimes it allows us to think easily in terms of non-deterministic automaton. Okay, so and then we'll see that in fact they are equally expressive and so on. Okay, any questions so far? Okay, good. So Tefila, is it clear? Any question?
No questions.
Okay, good. Thanks. So let's talk about non-deterministic automaton. So what is the idea of non-deterministic automaton? So essentially, you have, so we call it NFA, non-deterministic finite automaton. So the idea is that the NFA can guess transition on a particular input letter, So there is no need to write anything, because as I'm doing, I'm just going to share my handout, so you can just listen to me and interrupt me whenever you have a question. I think that is the whole idea, right? So like DFA, you have a finite number of states. So just one thing I can ask all of you is, so have you already done a course on finite automata? And so Ankit, Ishika, so I know that Tefila, of course, you have done courses.
I have done some basic course on Automata. Actually.
Sure. Okay.
So I
Okay.
know
That would
a
help.
bit of NFA. Yeah.
Okay. So what about you, Ishika? So you have this is like your first course, or you have done a course on automata theory earlier? So because I'm trying to kind of move a bit fast on these parts and
So in the fifth semester, we had automata theory course.
okay, okay, good. So so yeah, as I understand that all of you have some familiarity with automata, these things I'll try to move a bit faster. So now, what is the difference between DFA and NFA? So you have, in the case of DFA, you have this Q, and then cross sigma, you go to a single state, which is Q. Here, in the case of NFA, you can go to multiple possible transitions. So we have this thing, right? And so this is like finite number of, as in DFA, also you have finite number of states, and then you can have like a finite alphabet, and then like we will stick to like a single start state and so on, and a set of accepting states. So all these things are similar as in the case of DFA. Okay, so what happens in the case of NFA, this delta on this particular letter, it can return 0, 1, or multiple possible states the automaton can go to. The automaton can move to, right? So this is the idea. So yeah, so I think Ishika, you joined a little later. So what I would suggest is that like, so the handouts that I shared, you can try to figure out like about this shuffle and perfect shuffle. How do we do that? And if you have questions, you can always put them academically. So just to give you a simple example, so suppose you have this automaton. So what does it do? So I'm constructing this automaton where this is a language. It's a language of strings that end with AB. Okay, so how would you do that? You have like, you can have A comma B, and then you can say A, you go to some Q1, and you go to a B, and you go to Q2, right? So this is a non-deterministic automaton. Why? Because you have two transitions on A, you can either go to Q0 and or Q1. Now, the question is, suppose you have an input of the following form, let's say B, A, B, B, A, B, B, A, B, right? And in case of a non-deterministic automaton, there can be several possible runs, right? So you can see what are the runs here. On Q0, you can, on B, you are going to Q0. On reading this A, there may be two possibilities. Either you go stay at Q0 or you go to Q1. And then after reading this B, again, you can go to Q0, or you can, from Q1, you can go to Q2. Okay, so this is like BAB. Then we are reading another B. So I'll just move it a bit to the left. Okay, so then we are reading another B here. So again, from Q0, you go to Q0, and from Q2, it's kind of stuck, right? So this you cannot do anything more. And then from Q0, you read an A, you can either go to Q0, or again, you can go to Q1, you read a B, and so then you can stay at Q0, and here you can go to Q2, correct? So if this is the case, then we see that there are multiple possible runs. Some run might get stuck, and then there is some run which is not really reaching an accepting state, whereas there exists some run which reaches an accepting state, correct? So we say that a word is accepted if there exists a word is accepted if there exists an accepting run, correct? Good. So nice. So here, this is the kind of, so if I have to say, this is exactly the accepting one. Hence, this particular word is in the language of this automaton. Clear? So as long as there exists one accepting one, so we can say that this corresponding language, the corresponding word will be accepted by this automaton. Right. So again, just to give you the formal definition, you have an NFA, and in the NFA, you have these components Q, sigma, delta, Q0F. Okay. So Q is the set of states, sigma is the finite alphabet, delta is the set of transitions, and this is Q cross sigma 2 raised to Q, because you can reach a set of set of states. Okay. And F is a subset of Q. Okay, so now you see one thing, like, so the next question, whenever we are looking at let's say a new model of automaton, right? So you have two different, so we are looking at two different models of automaton. They are accepting similar kind of languages. So one question that people would ask, that whether they are equally expressive, right? So this is the question, that the first thing that comes to your mind, are they equally expressive, right? So whenever we are looking at two different kinds of automata, but they are accepting languages over the finite, like the same finite alphabet. So the questions that in automata theory community, people would study, they are expressiveness, as well as, for example, succinctness, right? So we are going to study these two things hopefully today. Okay, so these questions, so, and these are the questions in the context of NFA and DFA. So we are going to compare them. So you possibly already know that in terms of expressiveness, NFA and DFA are equally expressive, whereas in terms of succinctness, we will show that NFA can be exponentially more succinct than DFA. Correct? So any question so far, like about the expressiveness and succinctness? So for example, you can also think of, for example, so if you are already familiar with push-down automaton, right? So similar questions also you can ask in the context of push-down automaton. So for example, you can have a push-down automaton and you can have a deterministic push-down automaton, right? So, and you can ask exactly similar questions. Are they equally expressive? And whether one is more succinct than another. Okay, so we are also going to look at these questions for push-down automaton when we are going to study them, and we'll see that in fact for push-down automaton, the situation is not the same. So it can actually be the case that push-down automata, non-deterministic push-down automaton, can accept more languages than what deterministic push-down automaton can accept. So it essentially means that this is more expressive than this one, right? So this is what. So, but okay. So now we'll come back to NFA and DFA. So just as we did for the case of DFA, so we'll also define here the extended. So we can, if you remember, we defined this extended transition relation, right? So this extended transition relation, which is of the form delta star, correct? So what is the type of delta star? So as I said, whenever we are defining a function, so we will be defining first, like we'll be declaring its type, and then we'll define the function, right? So first is the declaration, and then it's a definition. So can you tell me, like, what should be the Q cross 2 raised to Q, right? So Q cross, again, it's exactly, so Q cross sigma star to 2 raised to Q. So if you recall, in the case of DFA, it was a bit, so this is for NFA. In the case of DFA, it was slightly different, Q cross sigma star to Q. So what does it mean? So you start from some state and you read a string and where you are going. So in the case of NFA, you can actually go to multiple such, after reading the word, you can end up in multiple possible states. Whereas in the case of DFA, you will just end up in a single state after reading the word, because it's deterministic. Clear? So Ishika, are you able to follow me? Any questions? So Ishika, I would just kind of encourage, like I encourage everyone to turn on the camera, because kind of then we can interact a bit better. I can also see you, and you can also kind of ask questions. I think that way it's slightly nicer. So are you able to follow me?
Yes, sir, I'm able to follow you. Sorry, I cannot like switch on my camera right now.
Okay, sure.
Yeah.
So okay, so now let's define the delta star. So Tefila, do you want to say how can we define this delta star? So what should be the definition? Right? So we are going to define this inductively, okay? So this is how. So this is like, so if you are in a state Q, you read epsilon, you stay there. But we have to write this. It's very important that we are using this set notation, right? Because this is 2 raised to Q. Okay. And then here we have delta star Q of WA. So what is this going to be? Can someone tell me? What is this going to be? Sorry, Bikhan, can you be a little louder? Sorry. Yeah, for NFA, how is it going to be? Can someone? Okay, very good. So suppose I will just make it a little simpler. Suppose Q prime belong to delta star Q comma W, right? So you are reaching, so essentially what it means, you are here in Q and then you are reading W, and actually like this is non-deterministic, you can reach several states, right? So I'm saying that this is the set of states where you can reach starting from Q by reading W. This is delta star Q comma W, correct? And now I'm saying that suppose consider such a member here, which is Q prime, and now you see where you can reach from by reading A from Q prime. Okay, so you can again go to multiple such states by reading A here. Okay, so it gives a set, and you take this union over all such Q prime in this delta star QW. Okay, so why are we defining this? Again, we'll see that this there is a purpose for defining this extended transition system. And can you tell me, can one of you tell me, like, what is the purpose? What are we going to use this for, this extended transition system? Sorry? Proving membership. Yeah, that is of course one thing. But here we were earlier talking about the expressiveness and succinctness, right? So we are going to use this for to show that this is indeed an NFA, the expressiveness of NFA is indeed equivalent to DFA. Correct? So we'll see how to use this. Is it clear, Ankit? Any question? I mean, if you have any question at any point in time, just feel free to interrupt and let me know, because I'm sometimes so any question, Ankit? Is it clear enough? Like this, the definition of extended? Okay, good.
Yeah, it's fine.
Okay, thanks. So now let's see how. So can you tell me then what is the language which is accepted by? Suppose this is my NFA. What is the language which is accepted? So this is the set of words W such that. Can you tell me what is the language accepted by this NFA? Is the set of words W such that? Sorry, Bikhan? Yeah. So how do I write this? Right. So delta star Q0. So Q0, what is the Q0? Q0 is my initial state. Correct? So Q0 is the initial state, right? So how I think I mentioned this. So what was the, how do you express NFA? Q sigma delta Q0 F. Okay, and then delta star Q0 comma W. So delta star takes some state and takes a string. And what does it give? It gives you a set of states, right? Delta star Q0 W intersection F not equal to empty. Correct? Is it okay? So this is so the language of this NFA is a set of words such that you get it. So these are definitions I'm pretty sure that all of you have seen. We are just trying to recall so that now when we kind of like get into the proofs and when we get into the other parts of the lectures, it's just a good idea, I mean, to kind of recall some of them. I mean, I'm pretty sure that all of you have seen this. Okay, now, suppose I give you this small exercise, okay? So what are we supposed to do? You consider an NFA, okay? And consider an NFA over the alphabet 0, 1, that, so this accepts a language. So NFA, this accepts a language. So what is the language? So the language is over the alphabet language L, over this alphabet L, such that the third letter from the end, is 1. Clear? Is it clear? Is the language clear? Okay, so you can say some yes, no, so that I can get to understand that you are following me. So just please be vocal. I mean, say yes, say no. I mean, I think it will just help me to, and I'll feel better. Like, okay, like, I mean, I'm also hearing, and it will be a much more interactive that way, right? So is it clear? The
Yes.
language? Yeah, very good. So thanks. So the third letter from the end is 1. So now if you have to construct an NFA, so what will be the thing? Can one of you tell me clearly? So how will the language, how will the automaton, the NFA look like? So this is my initial state. So what will you do? So the third letter from the end is 1. Right? So can one of you tell me how the NFA should look like? A simple one. Become. So when you are getting a 1, you guess that this is the third one from the end, correct? So you are guessing. So it is, so whenever we are talking about NFA, it is not just that the delta changes, but more importantly, what is important for an NFA is the power to guess, right? So this is very important, the power to guess. And this is what I'm trying to kind of elaborate in this example, that it can guess. Indeed. So suppose you see an N, see a 1, and you can guess that this is the third letter from the N. And then you can have either 0 or 1, you can have either 0 and 1, and you can reach here, right? And then this is my final state QF, and I cannot take anything from here. Like this is, I mean, no transition from here, which means this is like, if you read anything from here, that is like a rejection, correct? But now I have to read other things also. So what do I do? So Ankit, what should be the other transitions?
I think QF, if I read 1 at QF, then it will go back to Q1.
But okay, I mean, okay. So it can also be the case that I have already guessed it here, that this is the third last state, and I suppose I have guessed it correctly. So if this is the third last this thing, then I'm not going to read anything from here, right? So for example, suppose this is 1 1 0 1 0 1, right? So I'm saying that what I want to ensure here is that this one would, this is the third last, right? First, second, third. So this one would correspond to taking this transition, okay? And after this automaton, if it wrongfully takes this transition, maybe on this one, right? It's a wrongfully takes this transition, then it will get stuck. It will not accept properly, right? So this is the power of non-determinism. Right? So Tefila, can you tell me like what should I add? What are the other transitions I can add? So what transition can I add here? So, okay. So what can I do, Vikram? So I can add a loop here.
Yeah.
Okay. I can add a loop here with the 0 and the
0,
1,
0.
right? Correct? Very good. So I'm adding a loop here with the 0 and the 1. And you see now this non-deterministic automaton, what it will do, it will loop until it reaches like this, it will just keep looping here. And then when it sees this one, it will take this transition and then it will take this transition, right? So even if it has not seen like what is there at the like end, if it, so when it is taking this, when it is taking this transition, it doesn't know when the automaton, so it's here, it doesn't know how more for how much more time this input word is going to continue, but still it is able to guess this transition correctly. So in some sense, the automaton, this NFA, it has the power of like God. It can see the whole thing even before it has processed, right? So this is the idea of the non-deterministic finite automaton. Now suppose if it happens that instead of this word you have 1 0 1 and you have another one, right? Then when this NFA, when it sees again this one, it will not take this transition. It will take this transition and continue until it sees this one, when it will take this thing, right? So that's why we say it's very important to understand the concept of NFA. It is not just that syntactically it has multiple runs, but the semantically, I mean, the thing is that this NFA has the power to guess which transition to take in order to have an accepting run. This is very important conceptually, right? It's very important to conceptually to understand that this NFA has a power to guess which the DFA doesn't have. So as if even before it has seen the entire input, as if it knows what the input is going to be, and accordingly it chooses an accepting run. Is it clear, Ankit, Tefila, Ishika? Right?
Yes.
Yes.
Yes,
Good.
sir.
Okay, thanks. Now, so the question that we said, so the regular languages are accepted by DFA. Now it is easy to see that every DFA can also be seen as an NFA, correct? Every DFA can also be seen as an NFA. So this, I think, it's kind of easy to see, correct? So whenever you have a transition in the DFA, right, if the form is Q and on an A, you are going to Q prime. In the NFA, it's very important to write it in this way because it's a state of states in the NFA. But so what I'm saying is that you can kind of see a DFA as an NFA. But what about the other way around? Are DFA more expressive? Like, sorry, are NFA more expressive? So do NFA accept something, accept a language that cannot be accepted by any DFA? Cannot be accepted by any DFA? So this is the question for the expressiveness we would like to answer. The other way around is very easy to see. Now, what about this? We know, I mean, since all of you have already done a course in automata theory, you already know that this is not the case. So corresponding to every NFA, there exists a DFA, right, which will accept the same language. Now, the question is like, how do you prove this? Okay, how are you going to prove this? Okay, so any idea? How do you think you are going to prove this? Right? So how do we prove this? So for example, so you have all heard of this thing called subset construction, right? You have all heard of subset construction. So for example, let's say again, let me just quickly give you an example. So suppose you have something here, it's a very similar to the previous example. So it accepts all these languages over AB such that the word ends with AB, right? So here sigma equal to A comma B, and it's a set of words ending with AB. So this is an NFA here, right? Because there are two transitions on A. Okay. So now, so suppose I say that I want to construct a DFA. Can you quickly tell me? So you see that I'm putting this set notations here. So it's my initial state. What do I do? If I do a B, I go here. If I do an A, then I'm doing the subset construction. Again, so that's why I'm doing it kind of a bit fast. And right, if I do an A here, I would stay here, right? So because from Q0, right, from Q0 here, on A, I go to both Q0 and Q1, and there is nothing defined on A, so the A transition is not defined on Q1. So I stay at the same place because from Q0, I can go to both Q0 and Q1 and nothing is defined for Q1, correct? So Ankit, you are familiar with the subset construction? I mean, if you're not...
I'm not familiar with this idea. Like I know that for a NFA, there is a DFA, okay? And that DFA can be constructed if I take this Q cross Q, right? And
okay, so let me then tell you a bit about what is the idea of the subset construction. So for example, here, what we are doing, so here so we were exactly looking at this automaton, correct? So we are looking at this automaton strings that it may be. So what are we doing? So you have all these runs, right? You have these different runs, and we are now trying to construct a deterministic finite automaton from this NFA. So the state of the deterministic finite automaton, so first of all, it will try to collect all these states together. So for example, I will now have a deterministic finite automaton, which will say, starting from Q0, now I will go to Q0, then I will go to label my state, which will have both Q0, Q1. Because in the NFA, you have reached, the two runs have reached here. So I'll try to collect them together, correct? So this is so in the DFA, you have a single run, and the states that you are going to have in the DFA will collect these states together. And next, you will have the label corresponding to these two. So you go to Q0, Q2. And then here, again, where do you reach? From here, you go to Q0, right? So you go to Q0. Then you go to Q0, Q1. Then you go to Q0, Q2, correct? So this is the idea of the DFA. So there is a single run, but that single run will kind of keep track of all the different states which you are reaching across the different runs. So so in the DFA, we are going to construct, it will have a single run, but the DFA will have states of this form. So these are the states of the DFA, right? So the states are actually subsets of the states of the NFA, right? The states are actually subsets of the states of the NFA. So here, what were the letters? So it was B, A, B, B, A, B, correct? So that's why this construction, it's called a subset construction. Is it okay?
Yeah, it's fine, sir.
Okay, good. So so this is what we are doing. So on A, from Q0, you can go to both Q0 and Q1. So we are going to a state which is Q0, Q1. Okay. So now from Q0, Q1, if you read a B, where do we go, Ankit? Where do we go if we read a B?
Okay, so Q0, if I read a B, Q0 and Q2.
Very good. So I'll go to a state which is Q0, Q2. Okay. And what happens if I read, so we have defined AB, here also we have defined AB, AB. So now we have to define the transitions for, we have to define the transitions for this state. So what happens if I take an A from here, where do I go? Bikhan? If I read an A from here, where do I go? Is it true? Am I going to Q0?
if I read a, then I'll go to Q0, and for Q2 there is no transition if I read an A. So can we create a new state called dead state and take a combination of those?
No, I mean that if needed, but here where are we going? So you have to. So for example, here when we did, let's say when we did an A transition from here, right? So the A from Q1 you could not go anywhere, but from Q0 you could go to both Q0 and Q1. So you had a self loop on A. Clear? And so Tefila, where should we go by reading?
So
an
so
A?
Q0 Q2 on A goes to Q0 Q1 because Q0 on A goes. I think it would help if we say that we're taking the union of all the states that it goes to.
Exactly.
So if there is no transition on one particular state, then you would still end up in some other state.
Yes. Right. So I'm going to define that formally. But so as Tefila was saying, so what is happening from Q0, you can on A transition, you can go to both Q0 and Q1, which has this, and from Q2 there is nothing defined. So you come to this step. Okay. Right. So right. So and now what happens if I read a B? I go to Q0. Is it clear, Ishika? Is it clear?
Yes, sir.
Okay.
So to me, the idea is not clear. The why we are going to on reading it, we are going to Q0, Q1, and on reading B, we are going to Q0, sir.
Okay. So here is the while reading A, what is your question? So the question is that why from Q0, Q2 on reading A, we are going to Q0, Q1. Is that the question?
Yeah, that is my question.
Okay. So for example, here on Q0 in this NFA, so if you look at this NFA, okay, if you look at this NFA, by from Q0 upon A, where all you can go to Q0, Q1. Okay. And from Q2, this A transition is not defined. Right? So this A transition is not defined. So what we are going to do is for each of the states here, right, we are going to see which all states you can reach by reading an A, right? So we have this one, right? So essentially you can also consider like I take a union over all the sets I can go to. For example, if I had some other transition, suppose it's not here, but if I had some other transition, like, so instead of this automaton, if I instead had Q2 to, let's say, Q2 itself, correct? If there had been some transition like this, so if I had an A here, like a self loop, then you would have something like this, and then by taking the union of this and this, you would go to Q0, Q1, Q2, right? So what is the idea again? We are trying to figure out, right, where all you can go. So far, maybe suppose you are here, right? So far, suppose you are you have reached here, and now or suppose I mean okay. So suppose you have reached here, okay, and now if you have to read a B, then all we are saying is that we can only reach from here Q0, because from Q0 you can read a B and stay here. From Q2 this is not defined, so this run will die, and all we know is like the set of runs, all the set of runs currently we have after reaching this, where all we can reach, right? So this is what we are going to capture by doing this. Okay. So now we will formally define the NFA. Okay. So if you are given this NFA A, we are constructing a DFA A prime, and suppose what is the state space of so it is the NFA A, it's of the form Q sigma delta Q0 F, and here I have Q prime sigma delta Q0 F prime, So what is Q prime? So you are doing a subset here, right? So as you see, you are doing a subset here. So Q prime is clearly going to be a subset of 2 raised to Q. Correct? So it's a set of states, so it's going to be 2 raised to Q, and Q0 prime equal to Q0. And then what is my F prime? So what is my F prime? This we studied. Q prime belongs to capital Q prime such that sorry,
such that delta star sorry, it should be union of final states, right? No, it should be delta star Q prime comma W.
So what Ankit is saying is the following. So Ankit is saying, so delta star Q
comma W.
So Q, or you want to talk about Q0 or Q, the initial state?
Initial state, sorry, Q0.
Okay, delta star Q0 comma W. Okay.
Okay, and since this final state is a single state, okay.
Yes.
So it should be element of F.
Yes. It should be. So you see, like this delta star Q0 comma W, it's a set of states, correct? In the NFA. It's a set of states in the NFA, correct? And we say that as long as some run, there exists one run which is an accepting run, right? As long as one run reaches the final state, you will accept it, right? So this Q prime is actually of the form some Q1, Q2, etc. So this is the form of the Q prime, right? So I can say that Q prime such that Q prime intersection F not equal to empty. Is it clear?
Yeah, it's clear.
Okay, great. And now one thing we have to define is how do you define the delta prime? Okay, how do you define the delta prime? So how do you define the delta prime here in terms of the delta? Right? So you have a set of states. Okay. So in fact, what I'm going to do is instead of writing the braces here, let's say I use the square bracket to denote that this is actually a state of the DFA. So I'll use, instead of like this, I'll use this thing. Okay. So essentially it's the same thing, just to make sure that like we are particularly talking about a state instead of just the set of states of the NFA. Okay, so is this notation clear? So if I have, for example, I have a delta prime of, let's say, Q1, Q2, some Qi, comma A. Okay, suppose this is delta prime of this equal to, let's say I say this is P1, P2, some Pj. Okay, suppose delta prime equal to, when will be the case? When will delta prime of Q1, Q2, etc., comma A will be P1 to Pj? So we just saw this example a little while ago, right? So can you tell me?
When delta of Q1 to Q J on A goes to the set and goes to either of P1, P2 to P.
Yeah, very good. So I can write it in this form: if and only if delta Q comma A such that Q, so I'm taking what is Q? Q is an element of this set, Q1 to Qi. Okay, so remember that delta comes from the NFA. So delta comes from the NFA. So this is the NFA. So in terms of the transition of the NFA, I'm defining the transition of the DFA. So now I have delta of QA, Q belonging to Q1 to Qi, and what is this? This set is P1 to Pj. This set is P1 to Tj. Okay, so just take a look at this for a moment. What are we doing? So we have, for example, so there is some set of states. So the idea is the following. There is some set of states. So let me go to another page. So there is some set of states, okay, which you have reached starting from Q0. Starting from Q0, you have reached after reading something, let's say the W or word W, you have reached a set of states, which is like Q1 to Qi. And now we are saying that again from here in the NFA, after reading an A, you can go to some set of states, right? And we are trying to capture this set of states. We are trying to capture this set of states where you can go, correct? After reading the A from all of these. So what do? I take each of these Q1, Q2, right? And see where all I can go by reading A. And then I take the union over all these states. So this is what we have done. If you are already in this state, which is Q1 to Qi, then you see from each of these states, if you read A, where all you go, and then you take the union, and then you get suppose if you get this set, then it also you consider the corresponding state in the DFA. Right? Good. So now suppose I have to so this is how I am constructing. So we just looked at one example. Given an NFA, how do we construct the DFA, right? Given such an NFA, we saw how we construct the DFA. What we would like to now do, that indeed this construction is correct, right? So indeed the language accepted by A prime is the same as the language accepted by A. Where what is A prime? So A prime is the DFA. A prime is the DFA obtained by subset construction. Obtained by subset construction, and A is the input NFA, right? So what are we saying? So given any input NFA, you apply the subset construction. So given any input A, you apply the subset construction, and you get the A prime, and this is an NFA, this is the DFA, and we want to prove that indeed language accepted by these two things are the same, right? So the question is, now how do you prove this? How do you prove this? So how do you prove this? So what is the basic lemma we would like to show, Bikhan? So can someone tell me? So what is the first thing we would like to prove here? How do I prove this? Right? So can you think in terms of this delta star that we defined? Right? And this is my initial state. So what I would like to prove is that for all words X, okay, for all words X, delta star of Q0 prime comma X equal to some Q1, Q2, Qi, if and only if what? Can someone tell me? If and only if what? So this is in the DFA, right? So this is in the DFA. So we have Q0 prime, which is the initial state of the DFA, and this is a state of the DFA that you were reaching after reading X. So if and only if what, Tefila?
Delta of Q0 on X goes to
delta star of Q0 comma X. So we also had a similar, comma X equal to the set.
Q1 the set Q1 to Q.
Correct? Right? So this is, so we are talking about the set of runs in the NFA, the set of runs in the NFA And we are talking about the single run on the DFA, which is keeping track of all the sets of states at every step, right? And this we are doing for each X. Okay. So this is one thing. So we are saying that you would reach here. But now, so this is like, for example, I would call this a lemma. So this is my primary lemma. But this doesn't end here, right? You also have to say that if, then the next thing that you have to prove is that if X belongs to, or I would say X belongs to L of A prime, if and only if X belongs to L of A. Correct? So this is one thing we have to prove, and this is the second thing. But this might be very easy to see. The second part is very easy to see. Why? Ankit, why is the second part very easy to see?
Because of the lemma one.
Because of lemma one. Very good.
Yeah.
Because of lemma one. So you see that this thing is true. This thing, if it is true, and now if you say that if suppose X belongs to LA prime, what does it denote? It denotes that this after reading this X, the set that you have reached here, right? It essentially denotes that Q1, Q2, Qi that you have reached, right? This intersection F, correct? So suppose if you have this intersection F is not equal to empty by the definition of the acceptance of this. And here, if you look at, let's say, the DFA on the, or the NFA on the, so this is the DFA. The NFA on the other hand, you have X belongs to LA. Suppose the set of states that you can reach, let's say I call this some P, right? And then in the case of the DFA, in the case of the NFA, this is exactly if one of the states which is being reached is a final state, right? So if the set of states reached is P, then if P intersection F is not equal to empty. So this is the case for the NFA. If so, it means one of the states reached is final, right? And the first lemma gives you that P equal to indeed Q1 to Qy. Correct? So this gives. So the second part is very easy to prove. What about the first part? How would you prove this? The first part, you would prove using induction. Induction on what?
Induct on the length of X.
Yeah. Good. So we will prove this using induction on length of X. So okay, so this is the length of X. So we in the first class, I think we mentioned that this is the notation we are going to use. Correct? So initially, so suppose you have a base case. So I'll just talk about the base case, but I think the rest you can figure out. I'm not going to work out the whole details. So the base case is like this. Oops, sorry. So it's trivial for, I mean, I'll just say X equal to 0, right? So you have delta star. So essentially, it's on the NFA side, correct? So delta star Q0 comma epsilon equal to, so this is, here you have Q0 itself, correct? And on the DFA, what happens is like delta prime. So it is actually this, you get a go to a set of states, right? So delta prime star, and you have Q0, and then if you read epsilon, you go to the same states. So delta prime star Q0 comma epsilon, you go to. So this is on the DFA, right? So just to kind of, so that we don't have any confusion, so I'm writing this the state as in the square brackets instead of in the braces. Correct? So essentially you can see the base case, then you can say that induction it holds for some length of X. So in induction hypothesis, you will say that, oh, indeed the lemma above holds for some of all words X with length less than equal to some N, then you can do the induction step for W equal to some XA, correct? And you can prove this, right? From the definition of delta prime. So it follows from the induction step will simply follow from the definition of delta prime. So I mean, I would just leave it here because I would like you to work it out. I mean, just it will not take you more than 10 minutes max, even if you haven't seen it earlier. So if you just follow the definition, and I am also going to share the handouts, and the handouts will anyway have all the details, right? So this much of, I think like a few minutes you should spend on your own outside the lecture. And that will make you also more familiar and also help you to follow the class, correct? Right. So essentially, I'll just write maybe. So what essentially we are trying to prove that like, so we had this definition of delta prime. So delta prime star of Q0 XA, you will have to use this delta prime of delta prime star Q0 comma X comma A, right? So this is what I think you can sort of, this you can use and you can prove it. Good. So any question so far? Right? So, so what did we prove? Essentially the theorem. I mean, I did not give the entire details, but I think it's clear enough. Like, I mean, so for every NFA, so the idea is that like we are doing a bit, trying to speed up a bit just because we would like to get to the more interesting, because these are things many of you have already seen, and we will try to get to the more interesting parts. And if you have questions, just we have this Akadli, and you can put your, I mean, I would again encourage all of you to like post your questions and have discussions there. Right. So for every NFA, there exists an equivalent DFA. So what does the equivalent again means? So equivalent means that if the NFA is so equivalent, essentially it means that, sorry, it means accepting the same language. Same language. Correct? Good. So now, well, so what is the size of the NFA? So suppose if you have, let's say there are n states in the, sorry, what is the size of the DFA? So suppose there are n states in the NFA, n states in the NFA, how many states do we get in the DFA because of the subset construction, Ankit? Because of the subset construction, how many states do we end up with? Sorry?
I'm not able to, sir, able to visualize it actually.
So, okay. So in the subset construction, what did we do? So we had all the subsets, right? We were taking all the subsets, correct? So can you give an upper bound on the size of the
utmost to the power n?
2 raised to n. Very good. So at most it is, so in the DFA you have at most 2 raised to n states, right? Subset construction give you at most 2 raised to n states in the DFA, right? So this is because of the subset construction. You are right, right? So now I claim that, well, this subset construction is a bad algorithm because it gives you exponential blow up. We call it an exponential blow up. It's not good, right? Because you are giving me, let's say, a 5-state NFA, and I'm giving you back a DFA which has 32 states, let's say 2 raised to n. Is it good? It's not good, like, because it's I'm giving you a bigger thing. I mean, we like things to be concise. It's easy to understand it. So now, suppose I claim that, what is my claim? That I can come up with a better algorithm. I can come up with a better algorithm than a subset construction, which will give me a blow up which is less than. Claim is better algorithm. I have a better algorithm. I have a better algorithm that produces a DFA, produces a much smaller DFA, right? Much smaller DFA. Let's say of the size order n square. Okay. The question is, Ishika, can this be true? So do you think it can be true? Can I come up with a better algorithm? So Ishika, you were, yeah.
Probably, sir.
Probably yes or no?
Probably yes.
Probably yes. Yeah, because of what? Because?
Like, I don't know, when we are going from n states to 2n states,
2 raised to n
is it
state,
necessary that we are going to all of the 2n states?
Good question. So she's asking that, is it necessary that when you are going from n to 2 raised to n, is it necessary that all the states are necessary, right? All the states may not be necessary. That's true. All the states may not be necessary. For example, here we had 3 states and we got another DFA with 3 states only. It was not 2 raised to 3. We didn't need all of them. It's very good. But the question is that if I can show you that there indeed exists some NFA for which I can get like 2 raised to n, will that be good enough? Will that be good enough? So Tefila, what do you think? Like, so suppose I give you an example of an NFA, such that with n states and the DFA has indeed 2 raised to n states. Okay, is that good enough? And I construct this, is that good enough? So suppose I give you, there is an NFA, I do the subset construction, and that produces indeed 2 raised to n. Is the question clear? So suppose I do
fact,
the subset.
We could even take the previous example, I think, the one with the, I think the third letter from the right.
Yeah,
is,
right.
1.
So yeah.
Okay.
Yeah. So what Tefila is saying, that she's saying that you can take that example of the third letter from this, and if you construct the corresponding DFA, it will have 2 raised to n steps with the subset construction. Yeah. But does that answer my question? So if I say that indeed you start with, and is the question clear, Vikram? So I'm saying, so my claim is the following, that I can produce a better construction, better algorithm, right, which will give you less than 2 raised to n states. Now I'm saying, so what Ishika said is that no, it may be, you might have a better algorithm because not all of the states are reachable. Okay, so now my question is that suppose I give you an NFA for which you can possibly get all 2 raised to n states. Okay, and Tefila said that one example can be the one in which you had like the third letter from the end was a 1, right? We saw this example, and she's saying that, okay, for that, we will indeed need 2 raised to 3 states, maybe 8 states, and so on. Now, the question is that if I indeed have that, does it give an answer to my claim, like so that a better algorithm cannot exist because the subset construction is giving you this thing? Does it give you an answer? Exactly. So that in principle doesn't give you an answer to this, because you have to show that, well, I mean, then I can argue that there can exist some other algorithm which might give you something better. That is what I'm saying, right? So so that the mere subset construction give you 2 raised to n doesn't necessarily give an answer to this claim. So you have to show what Bikhan is saying. You have to show that there doesn't exist any DFA accepting the same language with states which is less than 2 raised to n. Is it clear? So what we discussed, right? So what we are now going to show is that indeed, like Ishika, so I hope you are following me. So what I'm saying, that indeed there exists. So suppose even if I say that there exists an NFA n for which every DFA has at least 2 raised to n states. Suppose there exists an NFA. There exists an NFA with n states such that every DFA has at least 2 raised to n states. So proving this is also sufficient. Does it give this thing like 2 raised to n? You need the 2 raised to n blow up. Is it sufficient? Is it good enough? there exists an NFA. Is this good enough, or there is still something lacking? So suppose I give you, so as Nifila was saying, that these 3 states here, right? So the third letter, or maybe it has actually 4 states, maybe, right? That example, it had 4 states, 1, 2, 3, 4. States. Okay, so if you had n states, so that had maybe 2 raised to n minus 1. But suppose if I have 4 states, you have 8 states in the DFA here, correct? But is it sufficient to prove this? So if I give you this one example of an NFA, you produce another DFA which has 2 raised to n minus 1. Is it sufficient, or do you need something more? N is a variable. Very good. N is a variable. Because if I just fix one NFA with some n states, I could have also said that this is 2n. It doesn't give you necessarily 2 raised to n minus 1. So hence I need a family of such NFA. Family of NFA for every n, right? So for every n, as long as I can get 2 raised to n minus 1, right? Then it will give you such a lower bound. Oops, something happened. Then it gives you a lower bound, right? That these many states are needed. Is it clear? You need a family of such NFA. So that for every, then you cannot, like if it is, so for example, if it is 4, 8, if you have 5, then you have say 2 raised to 4 minus 1, right? So 2 raised to 5, so this is 16, correct? Then it is no longer 2 times 5, correct? It is no longer 2 times 5. So if it is actually such an exponential, then you need to show, in order to show that, you need a family of examples. Clear? Any question? Ishika, are you able to follow me?
Yes, sir.
Okay, so what are we then saying? That we are indeed going to produce such a family of examples, and we show that indeed the subset construction in the most generic form, like there doesn't exist a generic algorithm which is going to be much better. Okay, so you are not going to have for a generic, like it can work something for some special cases, but you cannot have a generic algorithm which will give you something better than such exponential blow up. Is it clear? So what Ishika initially suggested is that no, there may exist some algorithm because some of the states may be unused in the subset, but indeed we are going to see that it is not going to be the case with a family of such examples of NFA, right? So what is that family? Now the question is, what is that family? And we are exactly going to see. So for example, so this is what we looked at. So I have another 15 to 20 minutes roughly. So this is the example we saw. The third letter from the end is a 1, right? And so this is the NFA with 4 states. So you can try to draw the DFA. Indeed, like, so this is the DFA, deterministic finite automaton. It indeed has 1, 2, 3, 4, 5, 6, 7, 8. So 2 raised to n minus 1 states. Okay, you can try to draw this yourself. Okay, so it indeed has this, and we are going to show that indeed if instead of L3, if I use L4, then we are going to have how many? 16 states. If you have L5, you are going to have 32 states and so on, right? So this is what we are going to prove. Okay, so suppose so essentially, how are we going to prove this? So suppose we prove this with contradiction, let's say. Okay, we are going to prove it. So Ln. So what is my language Ln? So it is so essentially the word over 0, 1, such that nth letter from the end is a 1. Clear? Now what we are going to, it is kind of easy to see that you can have an NFA with n plus 1 states, right? We saw this already. You can have an NFA with n plus 1 states. Now we are going to show that no DFA, every DFA So we are going to show that every DFA accepting Ln has at least 2 raised to n states. Clear? How are you going to prove this? Become what? So who is going to tell me now? How are you going to prove this? This is interesting, right? Do you find this problem interesting? Like, Ankit, does it look interesting?
Yes, it's an interesting problem.
Okay, so Ishika, do you want to suggest something? Like, how do you think you can prove this? Every DFA accepting this language has at least 2 raised to n states. Okay.
Sir, can we say that since the language contains only 0 and 1, so each state has to have either 0 or 1, so it will go to some, like on 0 it will go to some x state, and on 1 it will go to some y state, so there can be 2 to the power n states. Like we have 2 to the power n choices.
You have, like, where are you getting to? So Ishika is saying that you may have 2 raised to n choices. I did not fully understand, but where are you getting this 2 raised to n from? So what is the source of this 2 raised to n?
Since
in your
our
DFA?
sigma, since our alphabets are 0 and 1, we have 2 different alphabets.
So you have 2 different letters. So first of all, like, this is an alphabet. So I think you should be very clear with the notations or the definitions, nomenclatures. So this sigma is the alphabet, and 0, 1, we call them letters or symbols. Okay. You should not call 0 and 1 as alphabet. So the alphabet is the set. Okay, it's a finite set. So this is the alphabet. You should not say 0 is an alphabet. You shouldn't say there are 2 alphabets. You should say 0 is a letter, 1 is a letter, and the set is an alphabet. Is it clear, first of all?
Yes, sir. Yes, sir.
Okay, good. Now what is your point? So you are saying you have an alphabet, and then what do you do?
Then I'm saying that in an NFA, since there are n+1 states, so each state, when we are converting it to DFA, each state will go to, will have their 0 and 1 defined. And since it is a DFA, so we can say all the states will be unique.
Well, I mean, yeah, I mean, I think so. So she's saying that all the states are unique. You have the zeros and the ones, but I mean, I think it needs to be a bit more formal. So anyone has some idea? Tefila, do you want to suggest something how you can do this? How do you think you can? So can you try a proof by contradiction? So proof by contradiction. Suppose there exists a DFA. Suppose there exists a DFA with less than 2 raised to n steps. Okay. I'll give you a hint. So how many strings of length n can you find? Become? Can you be a little louder? 2 power n, 2 raised to n. So how many strings? The number of strings of length n. This is 2 raised to n. Is it clear? Like, so for example, if you have strings of, suppose n equal to 3, okay? If suppose n equals 3, then what do you have? 0, 0, 0, 0, 0, 1, etc., 1, 1, 1. So there are 2 raised to 3 equal to 8 such strings. This is what I'm talking about, right? And then I'm saying that there exists a DFA with less than 2 raised to n states for the sake of contradiction. Can you reach a contradiction now? By some PGL principle. So what happens if starting from the initial state of the DFA, right? If you read all these strings, then what happens by pigeonhole principle? Tefila, by pigeonhole principle, what do you get? You have 2 raised to n such strings, each of length n. You have less than 2 raised to n states. So starting
there'd be
from the
some
initial
state.
So
There'd be some state that the machine can be in after reading 2 different words. Right?
2 different words of length n. So what Tefila said is that if this is the case, then there can be some W1, there can be W2, such that W1, length of W1 equal to length of W2 equal to n, and they are not the same. W1 not equal to W2, correct? And you reach the same state Q by pigeonhole principle, right?
Yeah.
This is by pigeonhole principle. Right? So for example, let's say your n is 6. So I'm just giving you an example. Your n is 6. So for example, like you can have, let's say, you can have, let's say, 2 strings, 1 0 0 1 1, and then another can be 1 1 0 0 1 1. Right? So if these 2 strings are different, then you see that there exists an I, right? I, which is less than equal to 6 here, correct? So here I am counting my I from this side. So here I equal to 2, correct? So my I equal to 2. Now you are reading this string and this string. Suppose this is my W1, this is my W2. They differ in this position, okay? And you are reaching from starting from Q0, you are reaching the same state Q. Now what? What can you do? It is a DFA. What can you do? Now what can you do? So I'm very close. Now you should be able to tell me.
So it's the case that either of these words are accepted, right? So let's say that the language is, let's say, the nth letter is 1 in the second string and it's 0 in the other string. So if one of these words is accepted, the other word cannot be accepted. But then we said that both of them are going
to. For example, here my n equal to, as I said, my n equal to 6. So 1, 2, 3, 4, 5, 6. So this is also accepted. This is
both
also
of them
accepted. Both of them are accepted, right?
Yeah.
I mean, both of them are accepted by this DFA. But now you have like, so, but they have some letters which are different. And so what is there? So you have, maybe you have taken a separate path, Q0, W1, you have taken a separate path and you have reached Q here. And on some letters, they are different, right? And it's the same path and it's a DFA. And you know what is important in DFA? That starting from state Q, if you read something, right? If you read a string again, you are going to reach an unique state, let's say Q prime. Starting from the DFA, if you read something, you are going to reach a unique state, which is Q prime. Now what? If the next characters are the same. So what kind of characters would you like to think of? Sorry? Next I characters. Very good. So Bikhan is saying, so suppose now you read another next I characters from here. So you have already W1 and you have W2. But now suppose you read another I characters which are the same string. So let's say I read 0I. So I 0. Okay. So what is the string that I get now? So I had, again, let me write down again, 1 0 0 0 1 1. I add another 2 zeros. But this can be anything. Doesn't matter what I'm adding, as long as it's the same I characters. And I had 1 1 0 0 1 1 0 0. So I added 2 zeros, but I could have added anything. I mean, these two have to be the same, but could have been anything, right? Now, starting from Q, if you read the same string, here it is 0I, right? So I zeros, if you are reading I zeros, you are going to reach the same state. So you are here at Q, You are here at Q. After this, for both of them, it is a DFA. You are going to reach Q prime, the same Q prime. Correct? Now what? Ishika, now what? So Ishika, are you, yeah? So what?
Yes, sir.
Yeah. So what is the problem now?
Now the sixth character from the end are different.
Now the sixth character from the end are different. So 1, 2, 3, 4, 5, 6. No. So it was already the second. 1, 2, 3, 4, 5. So it was already the second one. So I think you should add maybe one less actually. So it was like this side it is 1, 2, 3, 4, 5. So you should add one more. So let's say you just have to add a 0 only. Okay. So I would say 0 I minus 1 is all you need to add. So it is Q prime, correct? So now you see that the sixth character here is a 0 and the sixth character here is a 1, right? So in this DFA, what is happening? So this language does not belong to L6. This belongs to L6, correct? Now this DFA, okay? So this DFA, and so it's reaching, starting from Q0, reading this thing, you are reaching the same state Q prime. Now this one should be accepted because this is in the language. This one should not be accepted because it is not in the language, but you are reaching the same state Q prime and hence the contradiction. Sorry, hence the contradiction. Is it clear, Tefila?
Yes.
Ankit?
It's
Ankit, is it?
Yes,
yeah.
Clear.
So yeah. So what did we do? We said that, okay, so let me again go through the proof once again. So we said that we wanted to prove this, that for this language, right? So for this, or rather family of languages. So it's again, it's very important. We are talking about this family of languages. Family of languages, which is parameterized on n. So I'm considering this language ln, right? So the nth letter from the end is a 1. Okay, so we said that there is an NFA which can accept this with n plus 1 states, and every DFA should have at least 2 raised to n states. So this is a lower bound proof. It's a lower bound proof, right? So you might have seen similar things like in comparison sort, you at least need n log n comparisons, things like that, right? It's a very similar kind of thing, right? It's just that instead of algorithms course, we are studying these kind of things in automata course, right? So now how do you do this? By contradiction, So proof by contradiction. So what did you say? That, well, let's say there are less than 2 raised to n states. Then we looked at all strings of length n. There are 2 raised to n such strings. And then as Tefila said, that there should exist 2 different strings of length n that will reach the same state Q from the initial state Q0. And then as Bikhan again said, like you can add some same string of particular length depending on where W1 and W2 differ, such that now what happens is like in one case, for this extended string, the nth letter from the end is a 1. For the other case, the nth letter in the end is a 0. So one is in the language, the other one is not in the language, right? And then, but since you reach the same state Q after reading W1 and W2, by reading the same thing as it is the case of a DFA, right? As it is a DFA, you reach the same state from Q to Q prime, correct? So you reached from, as we saw, you went from Q0, W1, W2, Q, and then you added a new string V, you went to Q prime, correct? And then it cannot be the case because one is in the language, the other one is not in the language. So this gives a contradiction. Good enough, right? Hence, every DFA should have 2 raised to n states, at least 2 raised to n states, And this we are getting for a family of languages. So this is important. So we have to prove this for a family of languages. And you cannot just do this for a single language, not just L3 or L4 or anything of that sort. You have to show this for a family of languages. Clear enough? Any question? Right? So we learned quite a few things. First of all, is like, how do we prove these lower bounds? You have to show that there doesn't exist any DFA. Okay, it is independent of the specific algorithm. Number one. Number two is we also showed that you cannot prove it for a single NFA, but you have to prove it for a family of such languages. Correct? So let me see. I had something something else. So this is an example. So what we would like to do is, so this is one example where we have this particular example, which is 0 star. So what is the language that it is accepting? So the language which it is accepting is 0 star 1. Correct? Can you see that? The language that is being accepted by this particular automaton, it is 0 star 1. Is it clear? Like, can you see this? Any question? Or no, actually it is, maybe I'm not correct. So 0 star, this is 0 plus 1, because I can have the 0, right? Yeah. So this is what we have, right? 0 star 0 plus 1. This is what we have, right? As the language, correct? So now 0 star followed by either a 0 or a 1. Now the point of this thing is that if we do the formal subset construction, then what we are getting is something which is as big as this one. I mean, you can try to do this yourself, that you have Q0, Q0, Q1, Q1, all these subsets you are getting 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. So we are getting such 7 states. Now, my question is that, can you get a DFA with fewer states? Can you try to draw it and get something smaller? So can you try to just take 2 minutes and tell me if you can get a smaller DFA? So this is the language 0 star 0 plus 1. Can you get a smaller DFA?
Sir.
Yeah.
I mean, this might be a silly idea. What I'm suggesting that in the run of algorithm, okay, in the run of NFA algorithm, for every state QI, okay, I can go to at most n states.
Yes.
But there are only n states are there.
Yes.
So n states are there. So n into n, that should be order of n square.
No, what? How do you get n into n? How do you get n into n?
I mean,
so you are going like at every step you go to some n states, but you are not going to all those n states, right? You are going to only a subset of those n states.
Yeah,
you are only going to a subset of those n states, right? And there can be 2 raised to n such subsets, right? So now, what we are saying is that so Ishika, you are going to tell me if you can get a smaller DFA, right? Possibly I'm asking you more because I'm not able to see you, and hence I'm asking you more. So can you get a smaller DFA for this NFA?
Sir, I really don't understand, how did you get 0 to 1? It isn't this NFA saying that it can only accept a single one. As soon as a 1 is seen, then it's done.
No, it's not necessarily. So there is a 0, 1, right? So here is a 0, 1. So for example, just the only 0 is also accepted, correct? And or it can be just a 1 is also accepted, but it also accepts 0, 0, 0, 1. It also accepts 0, 0, 0, 0. So there can be a 1 at the end, but if there is a 1 in the whole string, that 1 should appear only at the end. This is what it says. Is it clear? Or right?
Yes, sir.
Because you can take the 0, 0, 0, and then if you take the 1, then you reach a final state and it ends here. And this takes you a non-final state, like which is called a trap.
Then is it necessary for this trap to be used?
It's not
like
necessary.
We can just eliminate this, right? And
you
as soon as we eliminate this, we can have a smaller DFA, right?
But this is anyway an NFA, correct? Like, so my point is that
this is an NFA. And when we are creating a DFA using subset construction, we have an extra state Q2 in NFA, so it will have more states while we are drawing the DFA. But if we eliminate this,
you are right. Actually, you can also do that. So you can actually eliminate this, and then you can construct your DFA that way. And indeed, you are going to get something which is like I mean, that is the whole a smaller DFA. And how many states at most can you have in that case? If you suppose eliminate this, and then you you kind of draw the DFA, how many states you are going to have? At most 4 states. Good. So in fact, yeah, that is right. So in fact, you can have a DFA with 4 states, and this is just to show that indeed, like if I mean, of course, as Ishika was saying, that you don't really need this particular thing, but that was the purpose of the exercise, in the sense that when you construct a DFA, it does not necessarily produce the subset construction. Does not necessarily produce. The message is the following: the subset construction does not necessarily produce the smallest DFA. Correct? So you can have smaller DFA with just 4 states. Okay, so I'll just tell you what you can do is the following. So just if you just follow like your natural instincts in order to construct a DFA corresponding to this, so what it is going to accept? It's going to accept a 0. Okay, and then you can have arbitrary number of zeros, and it's also going to accept a 1 followed by this. So you can have a 1 here, but then just a single 1 is also accepted. Okay, and then you can say, since it is a DFA, now you will need a trap anyway. So you have to have this thing, right? And then you say, I have a trap which is 0, 1. So you see that there are 4 states here, and this indeed accepts the same language, 0 star 0 plus 1, right? And so, but you could have also drawn this just the way Ishika suggested. She suggested like, oh, I don't need this trap. I can just get rid of this, and then I do a subset construction. It has only 2 steps left, and then if you take the subset construction, 2 raised to 2 gives you 4 steps. 4 steps. Good. So is it clear? Any question? Okay. So Tefila, it's okay.
Yes. No question.
Okay. Good. Thanks. Okay, so this is a question that I asked in the last lecture. So suppose you are given a DFA. So since in the last lecture we were studying DFA. So usually in the DFA we have it's a DFA. You have a set of final states which is F, capital F. Now the question is that, can you construct a DFA with a single final state always? Yeah, DFA with a single final state. Can you always do this? Okay, so this is a question that I suggested in the last class, and this was for Dikhan, and so he says no. Why? Okay, so so I gave him a hint. So what was the example? So you know that it's a set of binary strings. So L, it's a set of binary strings such that the remainder is remainder when divided by 3. Okay, so you consider the decimal. Okay, you consider the corresponding decimal, right? So binary string such that the decimal number when divided by 3 leaves a remainder either 0 or 1, either 1 or 2, let's say. right? So you have seen this language in the context of like, I mean, if you have seen the notes that I shared, the handouts, there you have seen possibly the language where the remainder is 0. So which means that the binary strings are divisible by 3, right? And I've slightly changed the language to it is being either the remainder is either 1 or 2. Okay, so if you consider this language, you can actually show that you cannot have a DFA with just one state. Okay, so you have to work this out yourself. I mean, I'm not going to like, I mean, these are things possibly you missed in the last lecture, but I can also the last lecture is not available on YouTube because we couldn't record it for some technical things. But I'll be happy to, if you are interested, for those of you who missed it, I can also take it once some other time. Like, and it depends on, yeah, if you are interested. Right. So this is something that you should do. And in the next lecture, so I'll start with something like something called the epsilon NFA. And we'll also see what is the need for the epsilon NFA. So why is it needed? Okay. Sometimes, like as we started with the motivation for NFA, sometimes it is good in terms of thinking in terms of NFA rather than DFA. We'll see that sometimes it's also interesting to think in terms of an epsilon NFA. And it's more, I would say, sometimes convenient to think in terms of an epsilon NFA, where you have an epsilon transition instead of just an NFA, right? So, okay. So I think I'll stop here, and we are going to study epsilon NFA and why it is interesting. We'll have some interesting exercise which will kind of give us the motivation towards thinking about epsilon NFA. Just like for NFA, for example, we got the motivation, we started with the shuffle example, right? So closure of regular expression under the shuffle operation. And we saw that, like, yeah, indeed, it helps if you think in terms of NFA. We'll similarly look at some languages where we'll see that if we think in terms of epsilon transitions, it will be much easier to think of languages, right? So we will meet on Thursday at 9:30. And before we finish, any other question? And so, as I said, that if you want the lecture that you missed, which is the second lecture, and it's also not recorded. The first lecture is recorded on YouTube. You will find it. The second lecture, I can take it, and then it's okay for me if you want it also. Okay. So, any question before we finish the meeting? Ankit, any question?
No, sir.
No? Okay, good. Tefila, how about you? Any question?
No question. So I went over the lecture notes of 1 and 2, so I'm good with them.
Okay, great. And what about Ishika? You have any question?
Yeah, no, sir.
Okay,
no,
good.
Sir.
So what I would suggest is that I'm going to send out the lecture handouts, and yeah, you can take a look on Academy. I'll post the links. Good. Okay then. So I'll just stop sharing, and I think I should end the